Hello, welcome to our talk, Rendering Games with Millions of Ray Trace Lights. I'm Chris Wyman, and I'll be handing it over to Alexey later on in the talk. So I want to start off with a little bit of motivation to make you consider why you might want to move your direct lighting to use full ray tracing. And then I want to give an overview of an importance resampling, which is one way I think you can use to do complex lighting, like mini-light direct lighting, given limited compute budgets. Then I'm going to pass it to Alexey, who's going to talk about how to take importance resampling and make it performant and robust so that you can add it to modern game engines. And then he's going to end with a brief discussion of our SDK roadmap for an upcoming SDK called RTX Direct Illumination, RTXDI. So if there's one thing you take from this talk, I hope it is that ray tracing enables new lighting that exceeds the limitations imposed by rasterization. And hopefully you've seen this Marbles at Night demo from our Ampere launch, which really, I think, exemplifies the sorts of lighting that you can achieve today or in the very near future with ray tracing at interactive and real-time rates. But what sort of limitations am I talking about that raster imposes? Well, real scenes contain potentially large numbers of light sources, many of them with all of them with finite area, not infinitesimal area. And these have complex visibility and shadows that extend throughout the scene. These lights can be dynamic. They can move around, they can split, they can merge, they can turn on and off, and they can change color. They can be arbitrarily shaped, they can be textured, and the textures can animate themselves. You might have, in particularly game scenes, you might have multiple disconnected rooms, each with their own sets of lights that are mutually invisible or potentially only partially visible between these two rooms, and that can be very difficult. And then the shadows affect not only your diffuse lighting, but also your specular lighting, as you can see here from the shadows of the boats off the water. And what we're trying to argue today is that real-time ray tracing can handle all of these dynamically in the very near future, perhaps even today. So let's talk about where we are. So rasterization, how it works, is it computes lighting for aggregations of pixels. So you compute, you amortize work over triangles, pixels on a triangle, pixels in an image or an image tile. And typically, when you do these computations, you use shadow maps for visibility, and there's one shadow map per light. Because these are expensive, you typically have your artists identify important light sources in advance that need a shadow map. Excuse me. And the performance comes from reuse and amortization of costs over triangles, meshes, image tiles, the full image, or even work launches. Now, for ray tracing, things are a little bit different. The light computations can actually be independent on a per-ray basis, and part of this is enabled by the fact that your queries can be independent, meaning they can sample independent lights for every pixel and for every ray. And because of this, the important lights can be selected at runtime. Now you might ask, where does performance come from? After all, ray tracing sort of has a reputation for being somewhat slow. But I'd like to argue that this is not necessarily the case. And part of this just requires changing your mental model a little bit to think about where performance can actually come from with ray tracing. And so let's talk about that now. How might ray tracing actually give you better performance than rasterization? I'd like to argue that this is actually pretty simple. The reason ray tracing can be faster is the queries are independent. And what this means is you can do work exactly where you need it, no more and no less. And optimization then becomes, how do I sample less, or how do I shoot fewer rays, whereas with rasterization you have to think about amortization, all sorts of complicated things like that. So let's do a little bit of a thought experiment here, and think about rasterizing a shadow map, which many of you are probably quite familiar with. And why might ray tracing give you better performance here? Well, if you think about a shadow map, and ask yourself, does the cost scale linearly as you go from a 1 squared shadow map here to a 4K squared shadow map over here? And obviously the answer is no. We all know that this shadow map over here is not 16 million times the cost of this one over here. Maybe it's 16 or 32x, or maybe it's 8, depending on things. And so if you need a single query, that's a lot of performance to waste. And when you start moving up to more complex lighting environments, let's say if you have 10,000 lights in your scene, you don't really need a 4K shadow map for each one. You probably could deal with much coarser sampling rate. But unfortunately, these queries don't occur on a light space uniform grid, and a shadow map is a light space uniform grid. So it forces you to often do further oversampling and then post-process filtering in order to avoid aliasing and moire patterns in your shadow map. And this is sort of unfortunate. And really, this is an example of an observation I've heard a number of times from Eric Enderton that I find very insightful. I think of this as Enderton's law. And the observation is this, essentially: to get the more coherent your queries, the more work you're wasting. And to get coherent work in rasterization, just like in shadow mapping, we'll often perform unneeded computations, whether that's aligning things to a grid, whether that is helper pixels for 2x2 quads. But we try to get more coherent work, but this often introduces unneeded computations. And what Enderton's law is saying is amortizing over discarded computations isn't actually really a form of amortization at all. It's a form of wasted work, and you should just skip that unneeded work. And related to this is something, an observation. If you work with denoisers very much, you know that they work very well on smooth, coherent signals like diffuse lighting. And in those cases, you should really be sampling more coarsely. What Enderton's law is really saying is you should be doing the minimal amount of work needed to cleanly reconstruct your signal. Don't do more. That's just wasted work. And this is a very different mental model than with traditional raster rendering, and requires you to sort of change your perception a little bit on computations. Another consideration is that the key tenet of performance optimization, of course, is to make the common case fast. And so if you look in a shadow map rendering like, say, this one here, and consider what are the common cases are areas like this or this, where you have large regions of pixels that are fully lit or fully shadowed. And the less common case are regions like this, where you have high frequency variation in the visibility. But with shadow mapping, all of these regions have constant and actually relatively high cost. And as a researcher, a personal frustration of mine has been in this region here with the fully lit regions, that I have not been able to make those significantly faster than these other two regions. So you might ask, how does ray tracing help here? And again, this comes back to the fact that rays are individual queries, and while each one might be more costly, we can use significantly fewer of them. So let's look at this scene here where there's hundreds of lights, many of them large area lights like this sun globe. And I want you to focus on this yellow highlighted region here and ask yourself, how many shadows are actually visible in these pixels? And my gut intuition, just looking at this image, says there are no shadows in this region. But it turns out that's not actually true, right? The sun is perhaps partially occluded by this globe here, the Earth globe, and some of these LED lights are certainly occluded by these other hanging planets. And so you actually, it's interesting to think about here. How many shadow rays do you actually need here? It's clearly not hundreds, and it's not even clear you need any. But if you do need some, do they need to be unique from this central pixel to the nearby ones, or can you reuse a lot of work? Now, if you look in a different region like down here, the answer is a little bit clearer. There's 2, maybe 3 unique shadows, maybe 4, depending on how you squint. But so you could imagine that you could get by with 2 or 3 or 4 really well-placed shadow rays in these regions. And if you start looking over this entire image, or a collection of scenes like this, and start asking yourself, what's the maximum number of unique shadows visible in any pixel? The answer is never very large. You can never really see that many unique shadows in one pixel, which is interesting. And I think it's a key observation. There's a limited number of shadows that are clearly visible in each pixel, and I think this should provide a target per pixel shadow ray budget. After all, why shoot more than 3 or 4 shadow rays per pixel if you simply can't see anymore? And what this allows you to do is it allows you to scale your ray budget with human perception rather than scene complexity, which is great because human perception isn't doubling every couple years like scene complexity is. Now, of course, the key question if you do this is, how do you select the appropriate shadow rays? And if you've done much ray or path tracing, you know that the answer to this is, of course, going to be some sort of importance sampling. So what is importance sampling? Well, it's a well-known mathematical approach for focusing samples in more important regions. And so if you have an integral, the integral of f, and you're trying to approximate it with Monte Carlo integration and with importance sampling, you take some number of samples n, evaluate your function, and divide by the probability that you picked each of those samples xi. Now, a better p means you have fewer samples n that you need before this converges in a noise-free result. And for real-time rendering, it's really vital that you minimize the number of samples you need, because of this is related strongly to the number of rays that you need to trace. So typically, of course, in this situation, f here is our rendering equation, which can change per pixel because the lighting can be different. And our probability density p is defined by some algorithm that we choose for sampling our lights. A number of techniques exist for doing this. You could sample random light, you could sample preferentially larger lights or brighter lights, or you could sample preferentially in the BRDF lobe, since those are regions that are most important to this particular material. But none of these really give you what you want, which is a reduction of this number of samples to 1 or 2 or 3. Ideally, what you do is you use perfect importance sampling and select this probability p proportional to f. If you do that, you get cancellation and you're just left with this sum over the constant of proportionality, which reduces the number of samples you need to 1, which would be great for ray tracing if we can shoot just 1 ray per pixel. That would be amazing. Unfortunately, to achieve this, we need to know this constant of proportionality c, and it is equal to this integral f, which is what we were trying to solve in the first place. Fortunately, however, there's an approximate method that allows us to approximately compute c. And this technique is known as resampled importance sampling, and I'm going to get to that in a moment. But if I can approximately sample c, I might not be able to get by with 1 ray per pixel, but maybe I can get by with 2 or 3. So what is resampled importance sampling? It's also known as RIS, and I'll informally call it importance resampling, which is a little bit less of a mouthful. Now, perfect importance resampling requires you to know this integral, which we won't know. That's what we're trying to solve. But we're already approximating. We're already doing numerical sampling, so why not do it again? Why not approximate c as some Monte Carlo summation 1 over m times f over p? Now, if you're listening carefully, you'll notice that we seem to be going in circles, because after all, this is what we were doing on the prior slide before we started talking about RIS. But if you actually plug this back in and generalize a little bit, so we use p hat rather than f, to get a generalized formula, this is the estimator for resampled importance sampling for RIS. And this is interesting because it's introduced a new function p hat here that we can control, right? There's still f, the rendering equation. There's still p, our sampling probability for how we pick samples. But there's now this new p hat that gives us some control over this behavior, and it's actually arbitrary, or nearly arbitrary. And with p hat equal f, we get this approximated perfect importance sampling, but we can choose other values here as well. So I've been diving a little bit into the math here, which I may not be appropriate for all of you. So what's the TLDR? Right, the difference between importance sampling and importance resampling. So with Monte Carlo importance sampling, you do this, and your samples are better if you improve the sampling algorithm you have p. And that's really your only control over how you improve convergence, is by improving p. With RIS, you get this formula over here, and what you're essentially doing is you're taking m samples, some number of samples from p, and they might be kind of bad, but via the magic of statistical resampling, we're going to turn m bad samples from p into n good ones from p hat. And p can be extremely crude, but it really should be cheap because we're going to take a lot of samples from it. But again, p hat can be arbitrary, which means we can select it for optimal behavior. Behaviors like cancellation to make the performance faster. And one thing I want to point out is you're probably actually using resampling and don't realize it. So this might look complicated, but you already do this probably. MIP mapping, light probe sampling, upsampling, downsampling, multi-scale renderers, probably checkerboard rendering, are all doing things where you want one sampling rate, but you don't have it. So you go to a different sampling rate and then transform from one sampling rate to another. And that's really what importance resampling is doing. And so you already do this. This is just a new application that's stochastic rather than on a regular grid, and it's doing it for selecting shadow rays. So if this is so simple, why go into the math? The reason is I want to get to the key insight here, which is that resampling can occur iteratively. So we start here with importance sampling. We apply importance resampling, RIS, once, and now we have this function p hat 0, which we can control. But this summation here looks an awful lot like this one, which means we can apply importance resampling again, and again, and again, and again, and again, and each one adds a new function, p hat 0, p hat 1, p hat 2, that gives you the developer control. And what this allows you to do is inject domain knowledge into your sampling. Domain knowledge like these pixels are similar to this one, and so they can provide good information that could help me select better samples. So how do we use this? How do we inject data into the resampling to improve our shadow ray quality? So let's look at an illustrative example of how this might work. So this is a complex scene down here from an amusement park with about 3 million emissive triangles. Imagine for each pixel we pick 32 of them with some random distribution and then select one of those after doing some reweighting, and that will give us something that looks like this image down here. Not particularly great. However, we also know that the nearby neighbors in our image are also doing the same process. They're finding lights that might be useful for them, and if they're useful at adjacent pixels, they might be useful for us. So we can take some of the nearby samples and apply resampling again to help us improve the quality. So, and that looks like this. And in this image here, just like the last one, I was shooting exactly one shadow ray per pixel, but now this looks significantly better. And of course, I can realize that I don't just have spatial information, I also have temporal information. Last frame was probably pretty close, and so I can use that to resample temporally, and I get an improvement even further, still shooting only one shadow ray per pixel. And of course, I don't just have one prior frame, I have an animation of prior frames, and I can reuse over all of those frames and still shoot only one shadow ray per pixel, giving results that look like this. And again, this has over 3 million emissive triangles, and I'm shooting one shadow ray per pixel and getting results that look like this. Each step here is another iteration of importance resampling. So now let's get to the basic algorithm here. And this is an algorithm known as RESTIR from our SIGGRAPH paper this year. A RESTIR stands for Reservoir Spatial-Temporal Importance Resampling. So for each pixel, we're going to start off by selecting randomly some number of lights from the scene according to a distribution P. And then we're going to select one of those that's going to represent our shadow ray. And again, this is an example of importance resampling. Now, for our early prototype, and this is not the optimal approach, and Alexey is going to talk about ways of doing this better, but for our early prototype, we sample P using, we created an alias table as a pre-process, which lets us select lights proportional to their intensity in constant time. And so that's how we sample from P. Now, after we do this initial resampling, we look up the data, the light that we had in the last frame. So that means we had one light that we shot last frame. We have one light here from step A. We're going to pick between the two of them with some relative weightings. And this is another application of importance resampling. So we're going to get one shadow ray out of step B. And then in step C, we're going to look at some number of random adjacent pixels and pick between the lights they used, or they selected in step B, and the light we selected in step B. And we're going to pick one light here to pass on. So for final shading, for each pixel, we get one shadow ray from step C in this algorithm. We're going to shoot a shadow ray and then use the appropriate normalization from our RIS sums. Now, there's clearly a a blank spot here. And what we discovered is if we shoot a shadow ray right after step A before we start reusing it, this injects visibility information into our sharing, which gives a huge improvement in image quality. And this is the basic algorithm that's talked about in our SIGGRAPH paper. So where are we now? Well, we've built a simple, powerful algorithm for selecting high-quality shadow rays. But it has some rough edges. We've got some missing features that are required for productization, and there's some flexibility and robustness issues. And now I'm going to pass it to Alexey to describe our work improving this to make it more feasible for integration in production.